Today we are going to discuss some of the problems on bilinear transformation. First problem, a digital low pass filter is required to meet the following specifications. First one, monotonic pass band and stop band. Second one, minus 3.01 decibel cutoff frequency of 0.5 pi radian. And third one, stop band detonation of at least 15 decibels at 0.75 pi radians. Find the system function h of z and the difference equation realization. Verify the design by checking for the pass band and stop band specifications. First step, pre-warp the band edge frequencies omega p is equal to 0.5 pi radian and omega s is equal to 0.75 pi radian. Using t is equal to 1 second to get ohm dash of p and ohm dash of s. That is, ohm dash of p is equal to 2 by t into tan of omega p by 2. By taking t is equal to 1 second, we get 2 by 1 into tan of 0.5 pi divided by 2, which is equal to 2 radian per second. Then ohm s dash is equal to 2 by t tan of omega s by 2, which is equal to 2 by 1 into tan of 0.75 pi divided by 2, which is equal to 4.8282 radian per second. Second step, choose a Butterworth filter to meet the monotonic pass band and stop band requirements. Let us design a low pass filter to meet the following specifications. Kp is equal to minus 3.01 decibels, less than equal to 20 log of HA of J ohm dash P less than equal to 0 and 20 log of HA of J ohm S dash is less than equal to Ks is equal to minus 15 decibel. Then order of the filter N is equal to log of 10 to the power minus kp by 10 or 10 to the power minus 0.1 kp minus 1 divided by 10 to the power minus 0.1 ks or minus ks by 10 minus 1. Whole thing is divided by 2 log of ohm p dash divided by ohm s dash. After substituting into the above formula, we get order n is equal to 1.94. So we have to round off to the next integer value, that is n is equal to 2. Next, we have to find out second order normalized low pass butterfly filter having the transfer function h2 of s, because order is n, so it is h2 of s. And we know that sk is equal to 1 at an angle of theta k, which is equal to 1 at an angle of k into pi by n plus pi by 2n plus pi by 2, where k is equal to 0, 1, up to 2n minus 1. Since n is equal to 2, we get sk is equal to 1 at an angle of k into pi by 2 plus pi by 4 plus pi by 2, where k varies from 0, 1, 2, 3. So first we have to find out the value for k is equal to 0 and 1, and sk should be, when k is equal to 0, sk will be, by substituting into this equation, we get minus 1 by root 2 plus j into 1 by root 2, and for 1 we get minus 1 by root 2 minus j 1 divided by root 2. This is LHP, left half of plane of H2 of S. Hence H2 of S is equal to 1 divided by S minus S naught into S minus S1, which is equal to 1 divided by S plus 1 by root 2 minus J 1 divided by root 2 into S plus 1 divided by root 2 plus J into 1 divided by root 2, which is equal to 1 divided by S square plus root 2 of S plus 1. Let us find the cutoff frequency ohm C to meet the passband requirement. Then ohm C is equal to ohm P dash divided by 10 to the power minus 0.1 kp minus 1 whole to the power 1 by 2n, which is equal to 2 radians per second. Then the pre-warped analog low pass filter HA of S is obtained by using low pass to low pass transformation to H2 of S, that is HA of S is equal to H2 of S, and we have to replace S by ohm C, which is equal to 1 divided by S square plus root 2 of S plus 1 at S is replaced by S by 2, which is equal to 4 divided by S square plus 2 into root 2 of S plus 4. So next step, obtain H of Z by applying bilinear transformation, that is T is equal to 1 to HA of S, that is H of Z is equal to HA of S at S is replaced by 2 into 1 minus Z inverse divided by 1 plus Z inverse, which is equal to 4 divided by 2 into 1 minus Z inverse divided by 1 plus Z inverse whole square plus 2 into root 2, 2 into 1 minus Z inverse divided by 1 plus Z inverse plus 4, which is equal to 1 plus Z inverse square divided by 3.4142 plus 0.5858 Z to the power minus 2. This is the required answer. Next, we have to verify the design. Next is verification of design, that is the frequency response of the digital low pass filter is obtained by putting Z is equal to e power j omega in H of Z, that is H of e power j omega is equal to H of omega is equal to 1 plus e power minus j omega square divided by 3.4142 plus 0.5858 e power minus j 2 omega, which is equal to 1 plus cos omega minus j sin omega whole square divided by 3.4142 minus 0.5858 cos 2 omega minus j 0.5858 sin 2 omega, which is equal to h of omega is equal to 1 plus cos omega whole square plus sin square omega divided by root of 0.5858 cos 2 omega plus 3.4142 whole square plus 5858 sine 2 omega whole square. Hence 20 log of h of omega at omega is equal to 0.5 pi. If we substitute omega is equal to 0.5 pi, we get minus 3.04 decibels, and 20 log of h of omega at omega is equal to 0.75 pi, we get minus 15.44 decibels. Next, we have to realize difference equation. Difference equation realization. Let h of z is equal to y of z divided by x of z is equal to 1 plus 2 z inverse plus z to the power minus 2 divided by 0.5858 z to the power minus 2 plus 3.4142. Now cross multiplying, we get 0.5858 z to the power minus 2 into y of z plus 3.4142 into y of z is equal to x of z plus 2z inverse into x of z plus z to the power minus 2 into x of z. Now taking inverse z transform on both sides and rearranging, we get y of n is equal to minus 0.1715y of n minus 2 plus 0.2928 x of n plus 0.5857 x of n minus 1 plus 0.2928 x of n minus 2. This is the required answer. Next problem. A digital IIR low pass filter is required to meet the following frequency domain specifications. First one, passband ripple is less than equal to 1 decibel. Second one, passband edge frequency 0.33 pi radian. Third one, stop band detonation greater than or equal to 40 decibel. Fourth one, stop band edge frequency 0.5 pi radian. The digital filter is to be designed by applying bilinear transformation on analog system function. Determine the order n of Butterworth and Chebyshev filters needed to meet the specifications in digital implementation. It is given Kp is equal to minus 1 decibel ohm P is equal to 0.33 pi radian and Ks is equal to minus 40 decibels, omega S is equal to 0.5 pi radian. To find N for Butterworth filter, pre-warping the bandwidth frequencies omega P is equal to 0.33 pi radian and omega S is equal to 0.5 pi radian. Using T is equal to 1 second, we get ohm P dash is equal to 2 by T tan of omega P by 2, which is equal to 2 by 1 tan of 0.33 pi by 2, which is equal to 1.1408 radian per second, and ohm S dash is equal to 2 by T tan of omega S by 2, which is equal to 2 by 1 tan of 0.5 pi by 2, which is equal to 2 radian per second. Pre-warping does not change the values of Kp and Ks. Hence, N for Butterworth filter is log of 10 to the power minus 0.1 Kp minus 1 divided by 10 to the power minus 0.1 Ks minus 1 divided by 2 log base 10 of ohm P dash divided by ohm S dash. After substituting the values, we get N is equal to 10. Let us find N for Chebyshev filter. So first we have to find out discrimination factor D, which is equal to root of 1 minus ohm P to the power minus 2 minus 1 divided by, this delta P and delta S to the power minus 2 minus 1, which is equal to 5.0887 into 10 to the power minus 3. Next, we have to find out selectivity factor. K is equal to ohm P dash divided by ohm S dash, which is equal to 0.5704. Then filter order N is greater than or equal to cos hyperbolic inverse of 1 by D divided by cos hyperbolic inverse of 1 by K. and minimum filter order n is equal to cos hyperbolic inverse of 1 by d divided by cos hyperbolic inverse of 1 by k. So after substituting the values, we get n is equal to 6. Next problem, determine the system function h of z of the lowest order Chebyshev filter that meets the following specifications. First one, 3 decibel ripple in the pass band 0 less than or equal to omega less than or equal to 0.3 pi. Second one, at least 20 decibel attenuation in the stop band 0.6 pi less than or equal to omega less than or equal to pi. Use bilinear transformation. So we know that first step we have to pre-warping the band edge frequencies omega p and omega s using t is equal to 1 second. We get ohm dash p is equal to 2 by t tan of omega p by 2, which is equal to 2 by 1 tan of 0.3 pi by 2, which is equal to 1.019 radian per second, for Kp is equal to minus 3 decibels. Then ohm dash of S is equal to 2 by T tan of omega S by 2, which is equal to 2 by 1 tan of 0.6 pi divided by 2, which is equal to 2.75 radian per second, for Ks is equal to minus 20 decibels. Second step, let us design a pre-warp analog bypass Chebyshev type 1 filter having a transfer function HA of S to meet the specifications of step 1, that is the previous step. Then discrimination factor D is equal to root of 1 minus delta p to the power minus 2 minus 1 divided by delta s to the power minus 2 minus 1, which is equal to 0.1. Then selectivity factor K is equal to ohm dash p by ohm dash s, which is equal to 0.3705, and n is equal to order cos hyperbolic inverse of 1 by d divided by cos hyperbolic inverse of 1 by k, which is equal to 1 by 8. So we have to take n as, for the next integer value, 2. Let us proceed To find the transfer function H2 of S, because second order filter of the normalized second order low pass Chebyshev filter, that is Kp is equal to 20 log of 1 divided by root of 1 plus epsilon square, which is equal to minus 3, which gives epsilon square is equal to 0.9952. Then A is equal to half into 1 plus root of 1 plus epsilon square divided by epsilon to the power 1 by n minus half into 1 plus root of 1 plus epsilon square divided by epsilon to the power minus 1 by n, which is equal to 0.456. Then B is equal to half into 1 plus root of 1 plus epsilon square divided by epsilon to the power half to the power 1 by n plus half into 1 plus root of 1 plus epsilon square divided by epsilon to the power 1 minus 1 by n, which is equal to 1.099. Then sigma k is equal to minus a sine of 2k minus 1 into pi by 2n, and ohm k is equal to b cos 2k minus 1 into pi by 2n, where k is equal to 1, 2 up to 2n. Since we have n is equal to 2, we get sigma k is equal to minus a sine 2k minus 1 into pi by 4. Ohm k is equal to b cos 2k minus 1 into pi by 4, where k is equal to 1, 2, 3, 4. Let us find the left half poles of H2 of S. For that we have to take k is equal to 1 and 2 only, because the left half of plane we have 2 poles. So for k is equal to 1, we have to find out Sk by putting into the formula minus 0.3224498 minus j 0.77715. For k is equal to 2, minus 0.3224498 minus j 0.7771576. So this should be minus. So one will get positive and one will get negative. Hence H2 of S is equal to Kn divided by S minus S1 into S minus S2, which is equal to Kn divided by S plus 0.3224498 whole square plus 0.7771576 whole square, which is equal to Kn divided by S square plus 0.644899s plus 0.7079478. We have to find B naught is equal to 0.7079478 from the given equation, and B1 is equal to 0.644899. Since n is even, the normalizing factor Kn is equal to B naught divided by root of 1 plus epsilon square, which is equal to 0.7079478 divided by root of 1 plus 0.995263, which is equal to 0.50119. Therefore, H2 of S is equal to 0.50119 divided by S square plus 0.644899S plus 0.7079478. Since we need cutoff frequency ohm P dash, the required pre-warped low pass Chebyshev filter HA of S is obtained by applying low pass to low pass transformation to H2 of S. That is, HA of S is equal to H2 of S at S is replaced by S by ohm dash P, which is equal to 0.50119 divided by S square plus 0.6448996S plus 0.7079478 at S is replaced by S by 1.019, which is equal to 0.52 divided by S square plus 0.657152S plus 0.735105. So last step, step number 3, the transfer function h of z of the digital filter is obtained by applying bilinear transformation HA of S with t is equal to 1 second. That is, h of z is equal to HA of S at S is replaced by 2 by 1 into 1 minus Z inverse divided by 1 plus Z inverse, which is equal to 0.52 divided by 4 into 1 minus Z inverse divided by 1 plus Z inverse whole square plus 0.657152 into 2 into 1 minus Z inverse divided by 1 plus Z inverse plus 0.735105, which is equal to 0.52 divided by into 1 plus Z inverse whole square divided by 6.0494 minus 6.53 Z inverse plus 3.42 Z to the power minus 2. Now we have to verify the verification of the design. The frequency response of the digital filter is obtained by putting z is equal to e power j omega in h of z. That is h of e power j omega is equal to h of omega is equal to 0.52 into 1 plus e power j omega whole square divided by 6.0494 minus 6.53 e power minus j omega plus 3.42 e power minus j2 omega. Or magnitude of h of j omega is equal to 0.52 into 1 plus cos omega whole square plus sin square omega divided by root of 6.0494 minus 6.53 cos omega plus 3.42 cos 2 omega whole square plus 6.53 sin omega minus 3.42 sin 2 omega whole square. Hence 20 log of h of omega at omega is equal to 0.3 pi. If we substitute into the previous equation, we get minus 3 decibels, and 20 log of h of omega at omega is equal to 0.6 pi, we get minus 22.7 decibels.